Good evening, class. Today I'm going to start the next lecture of nanotechnology, science applications. Summary of week 7 lectures and problem solving questions will be discussed in this session. And I'm your presenter, Akshita Sharma from IIT Delhi. If you have any doubt regarding any of the question, you can raise your hands or even you can write your question or your query in the chat box. This is an interactive session, so it will be beneficial for both of us uh, that we interact in this session regarding the problems. So first of all, we will discuss the assignment of previous week 6 lecture. So the first question is, the band gap of a material is 3.5 electron volt. Predict its color. Your options are red, violet, opaque, transparent. So we need to understand, first you need to understand in which region this 3.5 electron volt lies. Does it lies in UV region? Does it lies in visible region, or does it lie in IR region? Then you will be able to answer uh, what is the color of the material. Anyone? Is it red, violet, opaque, or transparent? So the answer is transparent. Now you can tell me what is the energy electromagnetic spectrum. If you want to explain this question. No one? Yeah, it lies in UV region. Epoxy is the next question. Epoxy is a transparent polymer. Epoxy composites with microfiber as a reinforcement R. Opaque due to porosity. Opaque due to the formation of interfaces between epoxy and the fiber, or transparent, or none of the above. Epoxy is transparent, that we know. Then why the composite which we form with epoxy and microfiber is opaque or transparent? There first that you need to understand. It is opaque. And the reason of opacity is it porosity, or is it the formation of interfaces? Second answer. Silicon is used for solar cell application because it is an indirect bandgap semiconductor. It is a direct bandgap semiconductor. Is it commercially available in large quantities? Or your last option, it has a high bandgap. Correct answer is, first tell me what is it. It is an indirect bandgap or a direct bandgap? Silicon. It is indirect. Okay. But this does not solve our question. The question is asking, what is the purpose of using it? The purpose of using it, it is commercially available in large quantities. Okay. Next question. As the crystallite sizes decreases, More number of peaks appear in the X-ray diffraction. Second option, X-ray diffraction, peak shifts to lower angle side. Third option, X-ray diffraction peaks broaden, or both B and C. Crystal, here they mean the crystal sizes. Yeah. What is the correct answer? It was crystallite size. Okay. I have this XRD pattern with very sharp peaks. This is 2 theta versus intensity. This is in micrometer size. But what happens to when it changes into nano? What happens to the XRD pattern? XRD pattern looks like somewhat like this. Position remains same, but the peak broadens. See, here the peak has become broad because of the nano size. And we have discussed in previous class, this happens because the superposition of particle, the superposition of waves, the incident ray and the reflected rays happens also at the Bragg position, but even above, before, somewhat here also. This is a Bragg plane, but the superposition will happen in this position also and in this position also. Got it? These are the Bragg planes which satisfy the condition. But in nanoscale, these reflection also come into the picture, and hence we have intensity at that position, and it is reflected that the peak has become broad. Which of the following statement is not true regarding template assisted synthesis? It enables synthesis of particles with control size. Stable particles can be synthesized. Third option, it can handle only small number of particles in large template samples. Or fourth option, life of the particle will be limited. All of you understand what is a template assisted synthesis? We have a we design a template, like in lecture we discussed about Nafion based template, which has some sulfate groups and some water molecules, and that design, and that is a template we use in that for that synthesis. But which of the statement is not true? Yes, it enables control size. The way the Nafion polymer uh, sits through the substrate. Okay. Stable particle can be obviously this is a synthesis method, so we will synthesize stable particle. It can only handle small number of particles, yes, because most of the space is taken up by the polymer chains. We have only this much space for the template, we have only this much space for the template. Okay, so all three statements are correct, only fourth statement is incorrect. There is no dependency on the life of the particles. Which of the following features can be seen in the TJ result of the heating of Nafion from room temperature to 400 degrees Celsius? We have three statements, and you have to uh, tell me the correct statement. Removal of water, removal of carbon sulfur bond, breakdown breakdown of side chain and backbone. Which which of the option is correct? What happens at 4 degrees Celsius? Yes, we know this is logical thing. Removal of water will take place. So, using the option elimination, the option which has or the option which is having the statement 1 is correct. So we have three options left. This statement is incorrect. That we know. That is the way to solve the quiz like question. We sometimes go by option elimination. Second, removal of CS bond. Yes, carbon sulfur bond is weak. It will able to break down at 400 degrees Celsius. Overlapping. This is 2p orbital. This is 3p orbital. The bond. There is a weak bond. Okay. This is p orbital and this is large p orbital. Okay. So second statement is also correct. What about third statement? See, if at 4 degrees Celsius, side chain and backbone will break away, so there will be no natrium left. Got it? So only one and second statement is correct. So option 1 and second is correct. Next question. Match the following. XRD, you have this is experiment and you have to match with the output. So we have 4 experiment XRD, TEM. XRD stand for X-ray diffraction. TEM stand for XRD stands for X-ray diffraction. TEM stands for transmission electron microscope. TGA stands for thermogravimetric analysis. 4 probe measurement. What is it for? That you will get this answer from your output. So XID will give you crystallite size. We have seen there is a FWHM difference between micro and nano particles in XRD, right? That is because of crystallite size. TEM. What question will TEM will answer? It will answer particle size of the material. TGA. It is related to temperature. Will tell about the stability up to that particular temperature we want to test. 4 probe measurement. It is used for Conductivity. Who know about the conductivity of the sample? How do we perform 4-probe measurement? So, and the last of the remaining, the corrosion resistance does not match with any of them. I will come to 4-probe measurement later. Let's see which of the option is correct first. So, A belongs to fifth, B belongs to third, C belongs to first, and D belongs to second. So, option 1 is correct and other options are wrong. I will explain FOPO at the last. First, solve the assignment questions. Blue shift occurs when the particle size reduces. True or false? True. In general, when light is incident on a material, in general, when light is incident on a material, low energy photons get absorbed and high energy photons pass through. Is it true or false? It's absolutely incorrect. Vice versa happens. High energy photons get absorbed because they have more energy. Okay. And low energy photons just passes because the energy does not match. XRD and TM can both be used to measure particle size in polycrystalline samples. True or false? False. XRD gives crystallite size. Crystallite. TEM gives particle size and nanoparticles. This is my nanoparticles, of course. These are a lot of grains. This is has grain size. In next class, you will tell me the difference between all three sizes: crystallized size, particle size, and grain size. If you are able to understand, then tell me which of the size is used in Scherer formula. What does that formula account for? Out of these three sizes. We'll discuss this problem in next class. Okay. So I have to tell you what is a 4-probe measurement. We have a resistive setup. It's a tubular like structure, and here we put our sample. I'm giving you the zoom version. My sample is circular. We will make 4 metal contact the middle. Two wire will come, get attached over here. The two wire will come and get attached here. Okay, this is the zoomed version. This is connected to a PC, which is on which we are controlling some voltage within some range. Suppose I am giving the voltage from 1 to 10 volt. It will record the current's response. The feedback system will record the current response. Okay, and you will see you will get a straight line, I versus V. The slope will give you the resistance, because we know V is equal to I R. V by R will give you resistance, and resistance is dependent upon the resistivity. Sorry, 1 by R is equal to 1 by conductance. But we want to find out conductivity. How we will reach from resistance to conductivity? What is that relation? Anyone who knows that? Yes. R is equal to resistivity, length, and area. These belongs to the sample. Length of the sample, area of the sample. We know that area, pi by r square. We know the thickness, that is L. Got it? We know the resistance, we will get the resistivity. And resistivity will then give you conductivity. And what is the unit of conductivity? Simon. Okay. So in this way, 4 probe measurement works. What are, next question, what are indirect and direct band gap materials? What are they? How the band alignment position of these material are different? Okay, I'm drawing two systems and you have to tell me which of them belongs to which. This is my energy diagram. Okay, and this is E, energy, and this is pi by minus pi by. I'm drawing another energy diagram. Hmm. Drawing another energy diagram. Here also 0. This is pi by A, and this is minus pi by B. And the correspond, this is the two type of energy diagram. This is A, this is B. Which of them is indirect and which of them is direct band gap? This is direct band gap because the overlap, because the conduction band and valence band, the lowest point of conduction band and the highest point of valence band fall over one another. Okay, they are in the same position. Whereas in the indirect band gap, we can see these 2 points, the highest and lowest points, are different. There is a phase change. Here it is in pi by A position, and this part is in minus pi by B position. The band gap is indirect. Okay. And this is the corresponding band gap, the lowest and the highest. Not this and not this. And here, this is the band gap. Okay. What are the properties of direct and indirect band gap? What does it tell about? What does these two energy diagrams tell us about the optical properties of the band gap? The direct band gap semiconductor is efficient in absorbing radiation because it does not require energy. Both are fall in the same plane, pi by A and minus pi by A. And since the the electron has to travel from pi by A position to minus pi by B position, so there is energy consumed, and therefore indirect band gap semiconductor is less efficient in absorbing radiation. Moving on to the next question. What is the example of direct and indirect band gap? We have read about indirect band gap. The example, silicon is direct or indirect band gap? It is indirect, but it is still used in the fabrication of solar cells. Why? We know it is absorbing less radiation, but then why we are using it? Because it is commercially, it is uh, it is in abundance, and hence it is when it the overall cost is less. Not that less, but in respect to some relevant numbers, it is less. Industrial number, commercial numbers. Due to the abundance, it is used. Another example, the other semiconductors, gallium arsenide. Direct band gap examples, it is CDS, cadmium sulfide. It is widely used in the laboratory research, but yes, it is toxic. Okay, we have to carefully synthesize this material. Next question. Balls used in ball milling machine is made up of which material? Now we have come to the synthesis part. We have come to the synthesis of nano composites, and in that we have discussed synthesis using ball mill. So balls used in ball milling machine is made up of which material? It is made up of very hard material. The hardness and the strength is very high. That is tungsten carbide. We also use zirconium oxide. Okay, ZrO2. Next question. Explain the limitation of ball milling with respect to different RPM values. We have some limitation of ball milling technique. What is the full form of RPM? What does RPM stand for? RPM stands for rotation per minute. Okay. Then what is the limitation? if we, the question means that if we increase the speed, increase the RPM value, what, how will it affect the grinding of the of your reactants? If we decrease the speed, if it is in medium, speed is medium or intermediate, how will it affect the grinding conditions? So, suppose, let's understand it very well. This is a cylindrical tube of the ball mill machine. Here we have two rollers. Suppose ball milling is moving in this direction. This is, if the roller is moving in this direction, then the ball will move in this direction. Okay, these are the rollers. Rollers. This is cylindrical tube of ball. Okay. We have put, so we have the balls here. So I have 5 of them. Now think about the speed. If speed is less, suppose we have low RPM, and we have your samples in this, suppose like this. This is the sample over lying over here, surrounded. And if the speed is low, will we have the grinding action? The speed is low, it will move, the balls will move in this direction, and then it will come back to its place. There is no grinding happened, only rolling of the balls took place. No grinding of the sample was there. If it just got swirled back to its position, it swirled and then came back to its position. No grinding, and only rolling of the balls at low RPM. The grinding will happen when when the balls will reach at certain point and then drop. It will drop from that point over the sample, and this will happen with other balls also, and then we will have a friction leading to the grinding of the sample. Okay, talking about high RPM, then if we know that no grinding is happening at low RPM, then we should do grinding at very high RPM. Is it? Is my statement correct? High RPM. High RPM. Think about. Now the balls have, the speed is very high. Now instead of this position, now they are able to reach this position, B position. Okay, but will it drop? Will it get dropped from this position? No, because wait, sorry, because the gravity This is taking place over here is equal to the centrifugal force, and ball will never come down unless machine is stopped. It will go, it will roll over and over in a circular motion, but it will not grind your sample. It will simply roll in a circular motion, or we say rotate in a circular motion, because the gravity mass into acceleration is equal to the mw r omega square. So, we know that no effective grinding is taking place at low rpm and at high rpm. What is the case about intermediate or a medium rpm speed? Medium rpm. Medium rpm. It will be somewhat here in between these two positions, A and B, and then ball will have enough time to roll and then drop down over the sample. And this will happen with number of other balls also on your sample, and this action will give you effective grinding. So this is a limitation of the ball milling with respect to different RPM values. We are able to get effective grinding at certain RPM values only. It will not work at low and high speed modes. Next question. What is the purpose to perform ultrasonication and name the types of it? What is ultrasonication? What is ultrasonication? What is its purpose? And what are the types? We have to answer 3 questions in this one question. You have to understand 3 things to completely answer this question. What is the purpose to perform ultrasonication? And then name the types of it. Anyone? This is an interactive class, so if you know even the wrong answer also, we can discuss it. If you know incomplete answer also, then you can still answer the question. You can raise your hands or write your question or your answer in the chat box also. In ultrasonication, dispersion of the entity or the material takes place. Okay. If we want to distribute, it's a very layman's word, but to tell you the concept. Suppose we have some glass of water and we put salt in it. Okay. If you do not stir it, it will settle down for the time being, and you will not taste the saltiness of the salt, or when you sip the water, when you from the above, okay, you sip the few ml of water from the glass, you will not find the water as salty as soon as you reach down to the bottom of the glass. Okay, but If you stir it properly, vigorous stir, you will be able to disperse, you will be able to distribute the salt in all of the glass, in whole of the water, and hence the glass. And from wherever you sip the water, even from the bottom of the glass or even from the top of the glass, the saltiness will remain uniform. That is that is what ultrasonication do. You do that is the analogy you can draw for the ultrasonication. The stirring which you do with a spoon in ultrasonication, it takes place through the sound waves, through pulse, through ultrasonic waves. The frequency which we use is above 20 kilohertz. Okay, it is very sharp, and use pulse method. You will have some pulse, it will disperse your material into that solvent, it will again stop, then again the pulse will get on. It is a periodic, it happens in a periodic manner. So that is the definition and the purpose of ultrasonication. Are you able to draw that analogy? Do you agree with this analogy? Then an analogy of salt and water with the solvent and material of the ultrasonication. Name and the types of it. There are two types of ultrasonication. One is bath sonication, and one is probe sonication. What is the difference between these two? What is the difference between bath sonication and probe sonication? Welcome to the class, Shamnu Garli.
Yes, ma'am. Good evening, ma'am.
Is my voice clear?
Yes, ma'am.
Okay. Do you know what is ultrasonication?
By sending ultrasonic waves
Yes. What is the purpose of ultrasonication?
to disperse various substances above the frequency of 20 kilohertz.
That is the aspect of the ultrasonication. But what is the purpose of ultrasonication? Why do we do it?
By localized heat and pressure, we can.
Do you understand the ultrasonication? Like what we are using sound waves, right? What are those sound waves doing to your sample?
To disperse that samples that ultrasonication waves were used.
Okay, I have just explained one analogy. I will repeat it again. So tell me, in the end, tell me if you agree with that analogy. Okay. So I'm explaining the purpose of ultrasonication, and this will give you the definition of it also. You take one glass of water and you put some salt and you do not stir it. Okay, and when you drink that water, how will you judge the saltiness of that water? Like if you drink some few drops of the water from the above, will you have the same saltiness when you reach at the bottom of the glass to drink the water?
Top layer, some saltness will be there.
Yeah, will the level of the saltiness will be same?
No, ma'am.
No. But now when you have when you have stirred it vigorously, will the saltiness will be same or different all
Same,
over the
ma'am.
glass?
Same. Because it will be dissolved.
So that is the purpose of the ultrasonication. It is able to uniformly distribute your sample into the solvent. Okay, distribute the sample uniformly into the solvent when sound waves are when it pass through sound when sound waves are fall over that sample. The distribution is uniform to uniformly distribute. And why such ultrasonication technique is need? You know about carbon nanotubes? They are very long. They are nanoparticles. They are 1D nanoparticles, but they are very long. And if in a system I have multiple carbon nanotubes, they will get entangled. A bunch of CNT will form. And you also know that nanoparticles have high surface area.
Yes, ma'am.
And if I want to study some property with the high surface area, the nanotubes of a nanoparticle, and they are entangled like this, so most of the surface area is now covered. We are not able to get maximum surface area of each carbon nanotubes. Okay, so to detangle such type of nanoparticles and get the maximum surface area, we have to apply ultrasonication. When ultrasonication is applied, then each tubes get separated, get detangled, and now we can use these carbon nanotube for the purpose which we want to use. If you want to use for drug delivery, we will use. If you want to use for catalysis, like to enhance the speed of the reaction, in which surface area is much more important. Agree? So in such cases we use ultrasonication. Now coming on the second part of the question, name the types of ultrasonication. So have already mentioned bath sonicator and probe sonicator. What is the difference between these two sonication? Do you have any idea?
In that probe type, probe is immersed into the liquid for ultrasonication.
Yes.
For bath type, it was kept in a beaker. That matrix material, it was kept in a beaker in the tub like water. It was immersed.
Yes. Which is more powerful, bath sonicator or probe sonicator?
Probe.
Yes. Why?
Because with that probe, we can give force and we can dissolve with a force with that probe. So
Yes.
automatically all the particles will be get
Yes, you're
dissolved.
Yes, you are correct. So the term which you are saying, the term for what you are saying is cavitation. Okay. So the bubbles, the cavities, the bubble cavity of the bubbles are formed in the probe sonicator in much more faster, and the temperature is much more localized. because see, the probe here, the temperature is very high in the probe because it is radiating uh, sound waves. Here the temperature is localized. Temperature is localized, pressure is localized, and the bubbles are formed, have the are able to grow nanoparticles or disperse the nanoparticles with their pressure. In bass sonicator, the sound waves are coming from all the directions. So there is not one junction, not one single junction from which the temperature is being localized. Okay, so that is the difference. Which is tell me which type of sonication is suitable for small sample, probe sonicator or bath sonicator? Like if we have small amount of sample, so which technique shall I follow? If I have small amount of sample.
Small, we can use probe. Tub.
Oh, so which is effective, bath or probe?
Bath, I think so.
Yeah, right. Probe sonicator requires a lot of solvent, and sample should also be much more. In that you can only you have in the bath sonicator you have beaker of your choice. You can put solvent of your choice, and you can put your sample of your choice. But in probe sonicator, special kind of glassware is there. So you need at least that much amount of solvent to dip that probe. Okay, and you need more amount of sample so that it is the so it is able to distribute it properly. Okay, so that is why the bath sonication is much more helpful. Moving on to the next question. Now we are discussing one of the papers uh, which was mentioned in the lecture. So this is a elsewhere publication, and the journal name is Acta Materia. Paper is of around 2007. The title of the paper is Mechanical and Electrical Properties of Copper and Tantalum. TA stands for tantalum nanocomposite prepared by high energy ball milling. So in this paper we will understand the how ball milling technique is used in laboratory research, and on what factors like time, the amount of tantalum or copper we are putting, how does it affect. Okay, what does the abstract says? It says that they have used copper tantalum bulk nanocomposite, like they have made nanocomposite in huge amount with varying amount of tantalum. They have kept the amount of copper same, and then they have put some tantalum like 1%, 2%, 3% in this way. They have used high energy ball milling, and then followed by the sintering or compaction. That means sintering means that they have put it in a furnace. Okay. The final crystallite size of copper and tantalum during the high energy ball milling depends upon the deformation behavior of copper tantalum composite. So when we synthesize through solid state reaction, we we prefer to take the temperature around the melting point of the elements. Okay, following.
Yes, ma'am.
But when we are using the ball milling, then it is rather depend upon the deformation, like how the particles are being deformed rather than the melting point. Okay, melting point will be the secondary criteria. The first criteria will be deformation. Okay, So this is the another the grain size of the nano composite after sintering is less than 100 nanometer, that we will discuss. One thing to be note down is the hardness and compressive strength of copper tantalum nano composite is higher, 3 times, 3.6 times, 3.8 times higher than the micro composite that we have discussed, right? The hardness increases as the nano as we move on to the as the size of the particle decreases. Agree? That is the Hall patch effect. We have heard of what this is what Hall patch effect says. Inverse law of Hall patch. What does it say? If I have 5 nanometer and this I have 25 nanometer and this is the strength hardness or yield strength, 5 nanometer will be have more hardness, more strength as compared to the 25 nanometer. So this is being followed over here. Major contribution to the strength of nanocomposite from the nanocrystalline grain size. Obviously the contribution is coming from the most of the from the copper, because copper is in the more amount. Only we are adding 10-20% of tantalum. So the driving force for the strength is the strength of the nanocrystalline of the copper, which is in accordance with the Hall-Petch relation. So coming on to the characterization part like XRD, experimental details. So let me discuss some background for this paper. So why do we need to make this composite copper tantalum? Like why do we make first we'll answer why do we need to make nano composite? What is the application nano
Some
composite?
specific for some specific applications we can
Uh,
use by making the material composite.
Wait, just wait. I'm not able to listen to you. Just wait. Yes. What is the purpose of nano composite? Like applications? Yes. Yes, you were saying something.
For specific applications,
Yeah.
we will make nano composites
Yeah. For example, name some application.
like biomedical or
Think of the application which requires strength, which required some conductivity measurements, something like that. So we are discussing strength now, strength, hardness. So think of such applications like welding.
welding machinability.
Yes, welding requires lot of when we weld, we need strength. We do because we have to increase the strength of the material. Welding, blades. Sometime if you're talking about conductivity, then like thermal conductivity or electrical conductivity. So it can be used. These composite, nano composite, can be used in circuits like in laptop which we make circuits, okay, electrical circuits, heat exchangers, like if we're talking about thermal conductivity, we can use in x-ray components like because we know I've told you about copper k alpha is used, okay, that copper, I'm not talking about copper tantalum composite, but copper composite can be used, copper itself self only copper can be used in x-ray components, in cyclotron units, which require lot of strength, lot of hardness, because there are these are very huge and powerful. Followed. So these are examples. Like this is the purpose that we have to make nano composite, because copper might have see why we are making copper tantalum only here, because copper has here, as we can see, this paper has discussed that copper is able to give hardness up to 400 megapascal. Copper has the nanocrystalline copper has such a good property. It is giving such a good number of hardness value. Also, another paper claimed that pure copper with grain size of 16 nanometer shows a tensile strength of 800 megapascal. But then if it is giving such a good hardness, then why we are adding tantalum? There should be some purpose. Okay. The purpose is that copper the copper lacks thermal stability. Okay. The copper composite are not stable at high temperatures. So to increase that thermal stability, we add some another element. In this cases we are adding tantalum. And how the concept of Zener pinning comes over here? So Zener pinning comes when we use ball milling, right? Here copper particles have been broken down into smaller particles like this, irregular particles. And when we are doing ball milling, then tantalum particle sits through in this gap. Okay, then this smaller particles of tantalum acts like pins on the pins on the grain boundary of the copper. And then when we test this copper tantalum in thermal stability, then it does not break, because now because now the grain boundary has become stronger. And this is the concept of Zener pinning. When we use nanocomposite gains strength because of the Zener pinning. This only happens when we use the synthesis process of high energy ball milling. This will not happen if you use Zener pinning, will not come into the picture if you use sol gel method, if we use CVD method, if we use a vacuum plasma spray technique. Okay, this will only come into the picture when you use high energy ball milling. Got it?
Yes, ma'am.
Yes. So now you have understood why we are why we are studying copper tantalum, what is the application, what are the drawbacks of copper, and all other concept which we have discussed earlier, like inverse Hall patch effect, like hardness. Coming on to the characterization part. So this is the experimental details. So what they have to make copper tantalum, they have taken 99.7% pure copper powder and 99.7% pure tantalum powder. Okay, and the particle size is 45 micrometer. The particle size is 45 micrometer, and if I ball mill this, what should be the expected size of the particles after ball milling? Any range, any idea, any number you have in your mind?
Any one of the dimension should be for a nanometer means any one dimension should be uh,
Yeah, so any
within
number?
100 nanometer up to 10 to
Yeah,
100 nanometer.
right, exactly. But this will not happen immediately. Once you ball mill, it will come down to around say 20 mm. And when you sintered it, when you give it some temperature, sintering, then it will come to 10 nanometer size. Okay. During ball milling, it will come from micrometer to millimeter. And after you have given some heat, then it will come to nanometer range. Okay. So now moving on, they have used planetary ball mill. You understand what is planetary ball mill? How it is different from conventional ball mill?
But planetary, some balls inside that the three planetary balls were inserted.
Yeah, it is like a
It will rotate like an arbitrary motion.
the motion will be circular, but we have something like if you are talking about three mills, we can have four also. Okay, they're attached to one common point and it will rotate in that around that radius. This is the case of planetary ball mill. Followed, or shall I explain in this detail?
No. Follow.
Okay. Now what they have said, they have taken ball to powder weight ratio. So that is important. This is one of the optimization technique. So they are able to optimize that. If they are taking 10 balls, or so suppose they are taking 1 gram of sample. So the number of ball they should add should have at least weight of 10 grams. That is this ratio mean 10 is to 1. Only in that ratio they will able to get effective grinding. Okay.
Ma'am, once again, please, once again, repeat me
Yeah.
that one. That 10 is to 1.
Yeah, 10 is to 1. That is ball to powder weight ratio. It means that if you are putting 1 gram of sample into your ball mill, then you should take the number of balls which should have weight equal to 10 grams to get the effective grinding. See, 1 gram of sample is a lot of sample. And if you're just taking 2 balls or 3 balls, will it able to grind it well? Think. 1 gram is a lot of sample and you're just taking 2 3 balls. Will it give effective grinding, or a 1 gram of sample with at least 10 to 15 balls will give you effective grinding?
10 to 15 balls only.
So that is the ratio you have to play with. If you were taking small amount of sample, suppose you were taking 2 gram, so this number would be justified, like 3 to 5 will be good number. In that case, there is no point of taking 10 to 15 balls, because otherwise only balls will have will 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 what say will stumble upon each other and they will break eventually. Grinding will not happen effectively. So if you're taking less samples, so that in that we have to take less number of balls. If you're taking more sample, then you have to take more number of balls. There is no point in taking with less sample and more balls. Followed? So that is why this
Yes,
ratio is
ma'am.
important. Now tell me, they have taken toiline as an agent. They have put, this is a solid state method. Okay, they are grinding copper and tantalum, but they put some toluene also. Why? Why they're adding? I am only discussing copper tantalum composite.
It
Why
is
they
like
are taking?
to because in that ball mill, lubricant.
Yes, yes, you are right in right direction. Complete your answer.
To avoid friction and to avoid that
Friction should be there.
wear
Then
and
only
tear.
the sample weight. Friction should be there.
No, that to avoid wear and
Yeah, wear and tear of the balls.
yes.
Yes, and also to like sample sometimes sticks on the ball. So just to take out the sample, we need some liquidity. Okay, some liquid uh, liquid sample. So toluene is used. Can we use water?
No, it will be sticked with that. So not
It
be
will.
possible to. It will be sticked with the it will chemically react or
Yeah, it might chemically react. So toil, and also one more problem with the water, that it will not, suppose so once, what happens, toluene has a low temperature melting point, so it can evaporate easily. So it is easier to remove toluene from this composite rather than to remove water from the composite. Then we have to go up around 100 degrees Celsius to remove it. But the toluene, it can remove on its own at room temperature, like around 30-40 degrees Celsius. Okay, so even the removal of the sample, removal of the toluene is easy. We can use ethanol, alcohol. We can use acetone also. Okay, got
Okay.
it. Now discussing the what is this pattern? What is this technique I'm using in A part?
XRD.
Yes, XRD. So what does it says about that? They have taken uh, copper with 20% weight of tantalum, and they had taken XRD at different interval. And at the beginning of the ball mill, 0 hours, 5 hours, 10 hours, 15 hours, 20 hours. What is the change do you notice in the peaks when the time is being increased? Compare the peaks of
Sharp.
XRD peak as 0 hours and 20 hours.
In 20 hours, it was broadening. In
Yeah,
0 hour, it was a sharp
sharp.
peak.
So what is happening? Now the particles which were of around 45 micrometer, they are coming on to the millimeter size. They are moving towards uh, grain size reduction. Okay, that was the purpose of ball milling only. So that is purpose is solving. In this, through XRD we are able to prove it. Okay. Now B part.
Ma'am, one more doubt.
Yeah.
With that zero, it was sharp peak.
Yes.
So that size was same alone, ma'am.
Yeah, 45 micrometer. No grinding has happened at 0 hours.
No, that 45, it is in right side, na? Here, how you identify 45?
It was already like we can identify through SEM and
Okay.
TEM, but in the paper it was already mentioned it is 45 micrometer. They have identified through SEM and TEM.
But with that XRD, it's not possible to see na, that
No, in
45.
no, not through XRD.
Then with the 20 hours also, we cannot identify.
Sorry, what 20?
No, with the 20 hours also we cannot tell about that size. Na?
No,
With
no,
that
no,
XRD, then
We
with
cannot tell about size. We can only tell about the nature.
how either that size was uh, getting
Bulk.
reduced,
Yeah, yeah,
or that one only we can identify with that XRD. Na?
yeah. Qualitatively, we can only tell about size. Quantitatively, we have to go for SEM and TEM.
Okay, ma'am. In that 90 degree, that in that zero curve, beside right side,
Yeah.
only one curve is there in right side. 0 hour, na.
Uh, like
If you see right side of zero first curve,
this, you are
first.
talking this one.
Yes, ma'am.
So what is?
Only small
Yeah.
curves are there. Then with that 20 hours, that peaks were fully reduced.
Yeah,
Then
yeah.
what? Then that sizes was fully reduced like that. We have to identify, ma'am.
If we go for 30 hours, then it was possible that there is no effect now. So that is why they have probably stopped at 20 hours. It is not completely reduced because you are, since it is very high intensity, that is why you are seeing, you are able to see that it is a very low intensity. It is not completely reduced. It does not has completely disappear. It is still there. But if you compare with this, then you will find yes, it is disappeared. It is just a matter of reference. Yes, peak has broadened, intensity has decreased, but it has not disappeared as it is seems to you.
Only with that first and second curve only we can tell, ma'am. For the third peak, what we can understand with that, ma'am. First sharp peak in 0 hour, and 30 hour it was broadening. Then next that sharp peak has raised. Then again third one
You're
It
like,
has got
which
break.
peak you're talking about? Just tell me the range. Are you talking about peaks 30 to 50 range, or you're talking about peak in 90 to 100 range?
Range. In that first diagram only I am telling, ma'am. A
Yeah,
diagram only.
this is the diagram.
Yes, ma'am. For
0 around
30
you're talking
range,
about.
30 range, okay. 40 range,
Okay.
41, above 45 like that. One sharp peak is there.
Yes.
Then 50,
Yes.
50 also one.
Sharp peak.
Then we have to stop, ma'am.
No, we don't have to stop.
Uh,
We have to take the XRD of the full pattern, at least around, journal standard is 10 to 80.
oh, 10 to 80 degrees
Like
we
journal
have
we
to
have to
take.
do, but we can go below 10 and 80 also if we are having peaks after that. Most of the, like, you're able to solve XRD up to 80, but if you have some interesting peaks to see after 80, you can go above 80-degree also.
Oh, oh. So
Okay.
based on that, only two things we can, up to 50 range, we will get some shops like that. We can identify with the XRDM, ma'am.
Yes, yes, you can.
Okay, ma'am. Thank you, ma'am. Thank you.
But if you zoom it, you can see well. But if you are taking all the XRD pattern in the one graph, then it is will be difficult, and you are able to see up to only 50-degree.
Okay, okay, ma'am. Okay.
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 Now from graph B, they have fixed the time now. 20 hours is fixed. What now? What they are changing? They are changing the amount of tantalum. They started with the 5% and slowly increased to 30%. Now, what is the change you're observing when we are increasing the tantalum? Time is fixed, amount of copper is fixed. Only amount of tantalum is changing. What is the peak difference you're able to see in plot B?
Above 45, above 40 degree like that, um, that crystal size getting reduced.
Crystallite size.
Crystallite size getting reduced.
Yes, right. So the peaks are, if you see peak C, this is the peak at 5%, and this is a peak at uh, 30%. So peaks are becoming sharp, isn't it? Oh, sorry, I'm talking about tantalum. See the copper peaks. The copper peaks are black ones. See the copper peaks. When we are increasing 5 to 30%, the copper peaks are reducing. They are becoming more broad. That means,
In 5% it is getting broader, and 30% it is sharp.
no, no, no. That you are checking for the tantalum. If you are increasing the tantalum, you will see the black hollow circle belongs to tantalum.
Okay, okay, ma'am. Okay.
If you increase the tantalum, you will see sharp peaks of tantalum. That is what is happening. But see the copper peaks, na? That is our copper tantalum is a composite. So what is happening to the copper peaks? You will able to see much more clear at this peak. See, is it broadening or is it sharpening?
Sharpening, ma'am. In 30% it was sharp.
No, check, see properly of copper peak. See, this is copper peak
Oh,
dish,
C
and this,
diagram, ma'am.
sorry,
In B diagram only, na?
yes, this is B diagram. Check this. This copper peak, black dot resembles copper peak at 5%. You are able to see some peak over here, but you see it is very negligible in this at 30%.
No, you're telling above 70 degree, ma'am.
Yes, yes,
Okay, okay.
because here
Now
it is
I understood.
you're not able to see properly, that is why.
Okay, okay, ma'am. I
You
understood
can
now.
check this peak
It was
also.
broadening. Yes, ma'am. Yes, ma'am.
Check at 50%, at check at 50-degree. What
50
is happening?
degree in, with copper 30% it was slight broadening.
Yes, that is the purpose. Now you got it right.
So that size is smaller, smaller increased.
Yes, with increase of the tantalum content,
Huh.
the copper tantalum composite is decreasing. The grain size is decreasing.
Yes, ma'am. Slight
That is the,
decreased.
yeah.
Yes,
So
ma'am.
we are able to decrease size with two factors, with time factor and with the concentration of tantalum factor.
Okay, ma'am. Okay.
There are two ways. Okay.
Yes, yes, ma'am.
So how now
Time here they have not mentioned, ma'am. Only that composite percentage and
time is mentioned.
intensity.
They have fixed the time, 20 hours.
Oh, oh, sorry, sorry. You
First,
told it 20 hours. Yes, ma'am.
first they have fixed the time.
Okay,
Now
okay.
they have fixed
Mm.
the concentration of the tantalum.
Okay, ma'am. Okay.
Now they have now see this plot. This plot. Now they have plotted the crystallite size which we get from XRD. Okay, crystallite size, that is, it is reducing with the function of time. This is circular as copper and square shape is tantalum. So
Which diagram, ma'am? Sorry, which
this
diagram, ma'am?
one, this one, left hand side, A.
Yeah. Yes, ma'am. Yes, ma'am.
Now see, they have fixed the concentration. They are uh, this is a plot of 20% tantalum and copper. Now
Both
they have,
20%, ma'am.
sorry,
Both 20%. Copper also 20% and tantalum also 20%.
no, copper is suppose copper is 1, so tantalum is 1 of 20%.
Okay, ma'am. Okay.
Okay. Now see how the size has decreased over the time. This is a copper was of this crystallized size. See here we can see copper, copper tantalum, this copper this size and tantalum of this size, around 9, around 75 nanometer and 180 nanometer of copper, and size got reduced. And how they able to see 20, at 20 hours the crystallized size were matching of both of them. When the crystallized size match of both the copper and tantalum, that means the reaction will be effective. That is why we stopped at 20%. From XRD we are able to see it is broadening, but see here we are getting quantitative numbers around when the size reduce around 40 nanometer, which happens at only 20 hours. That is why this time is suitable for all of the uh, percentage, sorry, or for the 20% tantalum. Got it? Why didn't we stop 10 at 10 hours? Because the crystallized size was not similar. Why didn't we stop at we can stop at 15 hours also, it is very much similar. So that is the difference. We should not stop the ball milling before 15 hours. We can keep the time between 50 to 20 hours. But at 20 hours we are giving, yes, at 15 the size is matching, the crystallized size is matching, but at 20 hours the size is still reduced. Follow this graph. What you were saying now, from XRD we are not able to see the numbers, exact numbers. From this graph we can see the exact numbers. Okay? Yes, followed.
Yes, ma'am. That crystalline size is reduced based on that milling time
Based on,
and based on that copper ratio, copper with tantalum ratio and
yes,
milling time also.
yes. Now B, see B graph. It is similar graph, but now it is giving the, now it is covering all the percentages. 5%, 10%, 15, 20, 25, 30. See, the crystallized size. Uh, some information is missing over here. I think it is after 20 hours. Okay, after 20 hours So we were seeing the 30 at 30% we have highest peak broadening. Why? Because we have similar crystallite size of copper and tantalum at 30%. Here size difference is most in case of 5% tantalum. But as we increase in tantalum concentration, the crystallite size decreases, and that is why this is the best choice at 20R ball mill. Okay, and see this number is matching with this number. If we see it is around 40-45, this is around 40-45. Same value. This is for 20% tantalum. Sorry, see 20% tantalum. These both values are matching.
No, sorry to interrupt, ma'am.
Yeah.
Uh, what they are trying to tell, ma'am, with that with that percentage of copper and tantalum, that crystallite size will be reduced, like that they are trying to tell, ma'am.
Yes. We see in XRD we were able just to we are qualitatively analyzed. Peak was
Yes, ma'am.
broad.
Ah.
But what are the exact numbers? This graph is telling.
Oh, oh, oh.
Got it? The
Based on
numbers
that
were
size,
around.
based on that size, how it was, based
Yeah.
on that percentage, how that size varies.
Yeah. The numbers. How the numbers
Based on.
vary.
Okay, okay,
So
understood.
it was a. This is qualitative analysis. This is quantitative analysis. Okay. Understood.
First
Now.
one, first
Yeah.
graph A was quantitative, B one qualitative, ma'am.
This both XRDs are qualitative.
Okay, okay. This graphs were quantitative with that
Yes.
numbers. Okay, okay,
Yeah.
okay. Understood.
Okay. Now tell me this. Which image is this? Is it SEM image or this is TAM image? Is it SEM
This
image
one,
or
this one
sorry?
sim image, ma'am.
The uh, classic way to know is it a SEM image or a TEM image is that SEM image gives us the 3D 3D point of view.
Sorry, sorry. Tem only will give 3D image.
Sorry, SEM will give 3D and TM will give 2D. So is it giving you a 2D image or the 3D image? It is a 2D image.
2D.
You are only able to give the what is at surface. You're not giving the whole. You're not able to see the whole picture.
Yes, ma'am. Yes, ma'am.
So it is a 2D image, and this is a TEM image,
Tem. Okay, ma'am.
and it is a in TM it is a dark field. I have explained you two types of images: dark field and bright field. So dark field images are used when we are discussing the composite like metal composite, copper tantalum, aluminium copper. Okay, to be able to see where is tantalum, where is copper. So see, these white particles are tantalum, okay, and other particles are copper. What is this image?
Dark field image.
No, is it? Yes, you. It is a dark field image. Good answer. But what is the technique used to get this image? Like in this for this image, we have used TEM image, right? TEM technique we have used. What is the technique we have used to get this image? It is called. I'm not discussed it earlier. That is why I'm not able to answer. SED, selected SED stands for selected area electron diffraction. Okay, and I will tell you one interesting thing. Are you able to see these sharp peaks of copper and tantalum? This is tantalum, this is copper. Okay, these rings, it is saying na 200, 200, 111, 110. These number belongs to these four peaks. That is the beauty of selected area diffraction pattern. The ring structure, your some rings are there, right?
Pardon me. That you have told that 200 to 200 na, in which graph where we are
This
seeing
the
in
sharp
that
peaks.
in that TEM image itself, or
Nexadi, or see my pen over here.
yes ma'am, XRD, yeah.
A, XRD A.
Yes ma'am.
So this is 200.
Okay.
This copper is 200 again.
Okay.
So what is the purpose of saying one thing and same thing again and again? It means that we can verify our result from one technique and also with other technique also.
Okay.
Okay,
Okay.
you can get same number of some same XRD peaks as the this SED pattern. We
Ma'am,
can
here
verify
three
results.
peaks only there, na? Here three peaks, but here
Lot of peaks are
four.
there.
No, no. But how they identified first one 200, second one
Uh,
200
there is
like
some
this?
equation we have to use, so that is a lengthy process. We can
Okay.
discuss like
Okay.
whenever. It is very advanced technique. There are
Okay.
some formulas, and
Okay.
from that formula we can calculate.
No, no. Here, but with that, we are just seeing three peaks only in the diagram. But they have mentioned here four. That's what I am asking.
No,
Four.
it is in this diagram, like in this SED diagram, we are able to see four sharp rings, which belongs to four sharp peaks of the XRD. There were other rings also which belong to these high angle peaks, but it was not as visible. So they have only written four. We can write all of them.
Okay, okay, ma'am, that one okay, but here three only first three above 35, above 45, near 50, like that three sharp peaks we are seeing here, but they
Yeah.
have mentioned four 200, 200, 111, 110 like that. Now that's what I'm having doubt.
Okay. You are telling. Okay, you are saying that it is 200, but there is no 200 number here at 2 theta. That is what you are saying.
Yes, ma'am, three
Oh,
peaks.
see, every in XRD, every peak has the name. So this peak at around, which is around suppose 39 or 38. Okay, this peak is around 38. So this peak is 200 peak. That is the name of this peak. This is not the angle. Here it is the angle, right? These are not angle. These are planes, Bragg planes. Okay, we have
Okay,
discussed
ma'am.
the
Okay.
Bragg's law.
Yes, ma'am. Okay,
2D
ma'am.
n sine theta. So this n d was the spacing. Spacing was the between two planes. So
Yes, ma'am.
these planes are like for tantalum it is 200, copper is 11. So these are types of planes, and that planes we are reflected in the XRD pattern, and these peaks belongs to those planes only. Got it? Something
Yes,
is
ma'am.
clear?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
I hope it is clear. You can ask it again. Ask the question again.
Okay, that three picks for each and every picks they have some numbers, but
Yeah,
here they have given three
four. Yeah,
based on that place. They have given three,
yeah,
but what I have understood now is only three picks only visible. Might be some fourth one may be invisible, but they have given numbers like that. I have
Yeah, yeah,
understood.
yeah.
Yes, ma'am. Thank you. Thank you.
And these numbers are not degree. These are planes. Okay, got it. So
Oh, yes,
moving on
ma'am.
to the
Yes,
next
ma'am.
slide. So this is very easy. Here they are discussing the hardness of nanocomposite and microcomposite. So tell me from this picture, which is which is whose hardness is more, nanocomposite or microcomposite from this plot? From this plot, which hardness of which composite more, nanocomposite or microcomposite?
Nano composite.
Yeah.
Hardness
See,
is more.
and it decreasing with the increase of tantalum? Answer this
Increasing.
question.
Increasing, ma'am.
Right. Exactly. So you have followed this graph. Okay, and they have given the number. The hardness is higher, 3.6 to 5 points time higher. They have given the range of the hardness. Okay. Now, what is the other thing? See, do you recognize this graph? What does this plot says? We have discussed one numerical problem on this question. So what is this plot is?
Based on that D spacing,
No,
D
D is
spacing.
here. D is crystallite grain size. In this
Oh,
graph, it is grain size,
if
and here it is strength. So what does that plot mean? What the strength versus grain size plot? What that plot we call? What is the name of that plot?
if crystallite size decreases, compressive strength will be increased.
Yes. So what does that plot is?
Hall pitch, Hall pitch.
Yeah, Hall pitch. It is happening, right?
Yes, ma'am.
So that is the Hall pitch effect, inverse Hall pitch effect. And they have given all the number. What is the equation it is depend upon? Yield strength, yield strength constant plus slope and the crystallite size. This is the equation it is depend upon. Okay. Now moving on to the next question. What are the two major challenges? Now we are discussing the application of nanocomposite in drug delivery. So what are the two major challenges in drug delivery? What are the two major challenges in drug delivery? The
Transportation.
drug delivery in the body, not in the like the in the
Uh,
commercial space.
we
In the body.
cannot we cannot inject in a straight once for all. We cannot inject in one particular portion.
Yeah, you are partially correct. So that there are two challenges. First, that the target. It is not always possible that if we want to target one part of the body, it will the drug which we have injected will only target that part of the body. It is very much possible and happens that it is able to target all the body parts. Okay, not but the purpose of the drug is to uh, uh, the purpose of the drug is to sorry, what we say, the purpose of the drug to correct, or what the word is, the purpose um, to improve the condition of that infected part. But what does that drug do? It give its functions, or its drug to all other body parts also. So the target is the problem in the drug delivery. Got it? Understood?
Yes, ma'am.
And other is timing. and concentration. Suppose it is traveling through all the body and it has to target some corner or some deep nerves. It is might be possible that its concentration decreases through that time. Suppose your infected part wanted 25 micromilligram per ml concentration, but till the time it reached that part, it just able to remain only 10 microgram per ml. So to get 25, you have to increase more. If you say 50, if you inject 50, then it might able to reach 25, but increasing the concentration will affect other body part also. That is the challenge. Target and the concentration. Okay. Understood the two major challenges in drug delivery.
Yes, ma'am.
Okay. Now our aim is to understand how magnetism can be used in drug delivery through nanocomposite. So that is why the next question is based on magnetism. Explain the behavior of paramagnetic, ferromagnetic and diamagnetism with the help of H versus B plot and discuss the response towards H. So I'm drawing some plot. So you have to tell me from which material does it belong. B, H. This is suppose vacuum. It is not as straight but considered it. So this is A. See 1, 2, 3. So you have to tell me which line belongs to which magnetism. So, and do you understand what is diamagnetism? This is magnetic field. Okay. Now, do you know what? If I tell you the definition of diamagnetism, will you be able to tell me the answer of this question? Diamagnetism are those material which repel the magnetic field. So, now tell me, I have given you the definition. This is the magnetic field. Tell me out of 1, 2 and 3 which line belongs to diamagnetism. See, understand the definition. Diamagnetism are those material which repel the magnetic field. So, the plot which is far away from the magnetic field is which plot? 1, 2 or 3?
One.
No.
Oh, sorry. H only field, na?
The B is the magnetic field.
Then that three only far away from that magnetic
So,
field.
yes. So, 3 is belongs to diamagnetism. Okay. Paramagnetism. It attracts magnetism in the presence of when the current is passed through that material.
One will be paramagnetism.
We have other material also, no? Ferromagnetism. Ferro means obviously ferromagnetism imply that it is something iron related material, and we know that iron attracts magnetism. We have only two lines, 1 and 2. So which of them attracts more, paramagnetism or ferromagnetism? Which attracts magnetic field more?
Ferromagnetism will attract more.
Ferro. Is your answer is ferro?
Yes, ma'am. Ferro
So
will
one,
attract more.
so one belongs to,
Ferromagnetism.
right. and remaining is
Two.
paramagnetism. Understood?
Yes, ma'am.
So you now I have told you how does it behave, but we can look at quantitatively also. See, in the presence of this is magnetization. H is magnetization. With only smaller response of magnetization, the ferromagnetic material is able to attract so much magnetic field. It's able to attract the magnetic field towards it. Only see it is suppose it is 1, 0, 2, 3, 4, 5. Now read this plot 1, 2, and 3. If I give only around magnetization on 1, it is able the ferromagnetic material is able to attract so much of magnetic field. Okay, but to attract the same amount of magnetic field, suppose 20 Tesla it is a very huge number, but just consider it. If I so 2 Tesla. If I have to attract 2 Tesla in 2 and 3, then I have to apply this much magnetization. Sorry, to increase it. For this I have to apply around 4. For 3 I have to around up to maybe 10 magnetization units. Got it? Have you followed this? I am discussing this part. Discuss the response toward H. H. Small amount of H will give bigger values of magnetic field. But to get same amount of magnetic attraction from both the material 1, 2, and 3, the magnetization values has to be different. For paramagnetism, it is around maybe 4. For diamagnetism, it has to be much more than ferro and paramagnetism. So that is the response. So ferromagnetism will require less magnetization, then paramagnetism material require less magnetization, and diamagnetism material will require highest magnetization to give the same amount of magnetic response. Followed?
Yes, ma'am.
Okay. Now mark down the lines which mark down the line with corresponding magnetism behavior. So there are 3 colored lines. So you have to tell me which of them belong to super, para, magnetism, which belongs to ferromagnetism, and which belongs to paramagnetism. So tell me, blue colored lines belongs to
Blue colored ferromagnetism.
right. Blue color. No, no, wrong.
Blue, that violet ferromagnetism.
Yes. Green. Green belongs to
Green, dia.
green dia. Right. No, dia is not in the option.
Sorry,
We have
dia
4
one
options:
red.
super, ferro, and para.
Para.
And blue.
Blue is supermagnet. Super.
So yes. Now we will understand how to read this plot.
Yes.
Okay. See, what is the nature of ferromagnetism?
It will
So now
attract more.
let's leave it. Let's go to basic paramagnetism.
Hmm.
Paramagnetism materials show magnetism. Okay, why it is echoing? Is my voice echoing?
No, no, clear only, ma'am. You can explain.
Okay. So magnetism, paramagnetism materials show magnetism in the presence of magnetic field. If there is no magnetic field, there is no magnetism. So tell me, when the magnetic field is zero, so magnetism is zero in which case? Blue, green, or pink?
Green.
We have two cases. Blue is also no zero, right? See, this here magnetic field is zero. So magnetization is zero in two cases, blue and green.
Blue
See,
and
pass.
green. Both will be zero only.
Yeah, but there is only one material in the presence of zero magnetic field. It is showing some magnetism.
That ferro only it will
That
show
is
some
ferro.
magnetism. Okay.
That is see. Remember the definition. Apply that definition into that plot. So that is why we discuss the definition first. That is why I discussed the definition first over here, and then I gave you the problem. Remember the definition, remember the factors, and then see in that plot what factors are there, what definition they are talking about. This is a basic way to read the plot. Now we have two things. Now we have two options, blue and green. Okay. Now you know that in case of if it is paramagnetism, the magnetism value, the the value of the magnetism is less. Now you know it. Now out of three options you have cancelled ferromagnetism. Okay, now you're left with two options, super and para. Now you have to tell me which of them is super and para. And from the word name also, from the name itself you get, super means you must be having some larger values. Super paramagnetism, that is why you are getting that super word. Okay, so when you have some magnetic field which is giving higher value, green or suppose at this magnetic field which is giving you higher magnetization, blue
Blue.
or green.
Blue.
So that is why blue belongs to super magnetism. Okay, and hence the green one becomes paramagnetism. From the definition only we have solved this question through definition only. Followed?
Yes, ma'am.
Now coming back to the ferromagnetism, we have covered super and para. What happens? We will discuss what is super ferromagnetism, what is it phenomena, but listen the ferromagnetism first. So the classic nature of ferromagnetic materials are when the magnetic field is zero, they have some magnetization, and this point is called reminiscence. Remanence, remained, remaining, coming from the word remaining. Some magnetization remains. Okay. So if I want to remove that magnetization, I have to apply the magnetic field in negative direction to cancel out those magnetic moments. Okay. To cancel out that magnetic moments which are giving magnetism, I have to give the inverse of that magnetic field, inverse of those magnetic moment. That is why I change my direction. This is positive, this is negative. So to get magnetic field 0, I will give, to give magnetization 0, I have to apply magnetic field in opposite direction. And now since we have to force it, this points become coercivity, coercivity, coercivity. ठीक है? Got it?
Yes, ma'am.
Yeah. Similarly, if I want to now have some magnetic value, it will have some magnetization. So none. Okay. Got it? So this is why how you study the graph. Now last question. What is superparamagnetism? Superparamagnetism is that phenomena in which when ferromagnetic material is brought down to nano size, it no longer act as ferromagnetic material, rather it act as a paramagnetic material. Okay, when ferromagnetic material combines like reduced to nano size, then they behave they behave like paramagnetic material, but this value is very high. They have higher magnetization, so that is why we add word super paramagnetism. Got it? Followed? Last question. Is it
Is
poss is super paramagnetism possible in macro size molecule?
no, only my nano only it will be possible.
Yes. No, it is not possible. Any doubts still yet? We are done with
No,
the today's session. Any questions?
ma'am. Beyond that, some one question I am having, ma'am. In threshold value, some omega like that question is asked, but centrifuging while explaining that name was not mentioned, G or like that.
Tell me the question. You are not audible.
I think you may have not discussed today. I think in lectures, sir explained one thing,
Yeah,
centrifuging.
yeah. Mg versus this is a here.
That one I am not getting, ma'am. Mg G by R, root G by R. What does that mean, ma'am?
Oh, you're asking the assignment question, I think.
No, no. Just tell me what is mg. That enough for
Oh.
me.
M is the mass.
G
Mass.
gravity, yeah.
G is the gravity. So here they are comparing gravitational force
Huh.
and centrifugal force. So when the speed is high, high RPM is there.
Huh.
So at this point, the gravitational force and centrifugal force balance each other, and this is that.
Why you are trying, ma'am? I cannot get. Mg equal to m omega r square. Now
Yeah,
only you wrote, ma'am.
yeah.
Okay. No, but okay, I will try to understand once again.
You can
Mass
ask the
is
question now also, but in the next class also, like your choice. I can explain.
okay, ma'am. Okay.
Okay.
Thank you. Thank you.
So I will discuss the assignment of the you're talking about in next class, and that
Okay,
will be our
okay.
last lecture.
Okay, thank you. Thank you. Thank you.